Right, well, thank you very much to the organisers again. There's an ambiguity you may have noticed in the title. We'll find out whether it's for beginners or by a beginner. Thanks. If you've got low standards, you're going to love this. I've got some starting with. Okay, so what I want to do is take Bayesian probability theory as it's been used in the physical sciences, as it actually deals with data on the ground, and apply it to extensions of theories, and in particular to the multiverse, because I think there's some interesting results there about a number of the issues we've been talking about. As I've been discussing my views on probability with the various philosophers at this conference, the various looks of horror on their faces has been just delicious. I mean, just wonderful. So, this is definitely not, let me teach you guys how to do probability theory. This might be the other end of the spectrum of a convenient half-hour account of the kind of epistemic travesties going on in the physical sciences. There's a couple of places where I'm very interested in getting the philosopher's feedback, but let me do what the sort of physicists, let's just get on with it and worry about the details later on. So when probabilities are talked about in physics, there seems to be a number of different categories under which they come. This is not an attempt to categorize the philosophy of probability. This is just the sort of categories I've noticed that what might be called finite frequentism. The probabilities are just the relative frequencies of actual collections of events or things. That probabilities are really just descriptive statistics. So you have hypothetical frequentism, in which the relative frequencies of a hypothetical sequence. So if I say the probability of a coin flip being a half, that heads is a half. What that means is if I flip it an infinite number of times, that sequence will have a frequency of a half. I've called their objective chance. I was going to call it propensities and then got shot down by Barry at lunch the other day. Is the probabilities that are in physical theories. So I've got thanks to Barry, I've got a more precise definition of this. Objective chance, whatever Barry said. that I make, so it could be, I'm not going to distinguish between the sort of probabilities in statistical mechanics or in quantum mechanics, if there are any. But just that when chance is in a physical theory, when it's, say, the propensity of this thumb and this coin and that floor to produce a half when I keep flipping the coin. There's what you might call subjective Bayesianism, where you are quantifying the subjective state of uncertainty or certainty of a particular individual. And then there's objective Bayesianism, where we're talking about degrees of probability of a proposition given some state of knowledge. We're really trying to say, what does this piece of information say about that piece of information? So I first of all want to report something that's sort of happening in the physical sciences. My own personal sort of view on this is that I've never heard the word frequentism used except as the F word of statistics. That it almost always means naive, oversimplified, or just wrong. That Bayesian, on the other hand, Bayesianism often doesn't mean really Bayesian. Some people it just means correct. My impression was I see Bayesian all the time. I've never seen anyone defend frequentism. I just wanted to sort of test my own implications there, so I did just a search through the physics and astronomy literature. Title contains Bayesian. There are 6,500 papers. I did that 2 weeks ago, and there were another 500 papers. Title contains frequentist. There were 64 papers, of which 35 also have the word Bayesian in the title. Now, frequentist methods are often used and won't always appear in the title, so that's not necessarily a statement on what fraction of time the methods are actually used, but certainly no one is defending frequentism or advertising their particular statistical approach as frequentist. Why this is, I think, is interesting for various reasons. So Bayes seems to have a wonderful scope of what you can apply probabilities to. For example, if you want to answer the question, given observations, what we know, is general relativity more probable than Newtonian gravity? So on finite frequentism, the answer to that is no, so on hypothetical frequentism, it's also no, because it's not a statement about any particular sequence of things. On objective chance, it's no. because these are the probabilities, objective chance of probabilities from inside theories, so to speak. They don't stand outside theories and compare them. On subjective Bayesianism, maybe, how are you feeling today? What did you have for breakfast? Are you feeling okay? But on objective Bayesian, we can make a statement like that. And there's a lovely summary of this. So Ted Bunn summarized this as there are a set of interesting questions about the world, and then over there's the questions answerable by frequentism. So that frequentism flatly refuses to consider the probability that any scientific hypothesis is correct. So if there's a better option for probabilities, then we'd like it. And this is not a secret. I mean, Ronald Fisher is all but the patron saint of frequentism, and he said we can know nothing of the probability of hypotheses. There's a couple of other reasons why it really appeals to the scientists. So it's very practical. So astronomy in particular is a field which is staring down the barrel of the technical term is boatloads of data. Your average telescope will fill your computer's hard drive in a night. When the square kilometre array is built, it will fill your hard drive in about 1/10 of a second. The rate at which data comes from the telescope will exceed the internet. So it's that community, I think this is interesting, it's that community which has said, okay, things are getting serious, we really need to go with Bayesianism. In particular, there's a sort of a clarity and unity of method. It points to the right questions to ask, which is a very nice feature. So I've been thinking about this, that when you have a thought experiment in physics, say you've got two rockets and a string between them, and they accelerate in exactly the same way, according to special relativity, will the string break? Is this in your book? Yeah, okay. I forgot what the answer is. I think it's yes, but again. So it's an intuition pump that we can sit around and think about whether we really understand special relativity, which I obviously don't because I can't do that. That sort of example, at the end of the day, we can just sit down and say, all right, we've had a disagreement, let's just go calculate something. And there is a principled method by which we can calculate. And that is the sort of thing you get in Bayes, which you don't get in frequentist statistics. So Ed James gives the example of a 1970 textbook where they're looking at trying to fit a straight point straight line between data points with error bars in both directions. It proposes 16 different methods, which what you say about them is that they are not completely ridiculous, but then you can't say much more. It then is unable to choose between the methods, and the section of this textbook ends with the words, "This is all very hard." It's that sort of, I need to set a test for my likelihood, but which test? Well, it's sort of up to you, and if there's a whole load of things you could do, but no way to sort of choose between them. This comes from something called Cox's theorem. Instead of deriving probability theory statements from axioms, you start thinking about, okay, what would if I wanted to try and quantize this idea of plausibility that I got, that some ideas are more plausible than others. Why don't I set out some desiderata, say that these plausibilities are going to be represented by real numbers so that I can compare, that they will change in common sense ways, which really just gives the direction that more plausible is bigger numbers. That if a conclusion can be reasoned out in more than one way, every possible way must lead to the same result, that information must not be arbitrarily ignored, all evidence must be taken into account, and that identical states of knowledge, except perhaps for labeling, should result in identical assigned probabilities. Interestingly, if you start with those, you can actually derive then the laws of probability theory. And I highly recommend these two. You've got to sort of see it in action. These two papers here, get the references off me later. They're not difficult proofs, and I think they're very, very interesting. Sorry, Bernard, what exact time do I finish? I don't know when we started. 25, all right, I really want to finish early because some people are going to have something to say. Okay, so Bayesian probability. What we have then is that this probability function is a function between two propositions, the one that's given and A, so it is the probability that proposition A is true given the truth of proposition B, and it's being built up as extended logic. So classical logic is in there as special cases. For example, probability A given B equals 1 is the same statement as just saying that B implies A. In particular, it is not the statement that I know A, or that I'm certain about A, or that I've observed A, or something like that. It's just a relationship between propositions. If you want, so a good way to say that is, if you want to conclude therefore A, you need to add the premise B under here if you want to make that argument. In particular, there's no implication for the frequencies of experiments, right? This is about, what I'm doing here is theory testing, not theory building, right? That's a separate thing. There are, of course, objective chances we're going to have to put in our models, but that is not what this is. And in particular, it's not derailed by the fact that you don't know something. If you're just trying to quantify a certain state of knowledge, then the fact that something is missing from that is just a feature of that state. So you can build probabilities up from ignorance, which is great, because I've got loads of that. The goal is to calculate then the posterior. So this is that sort of unity I'm talking about. All you want to do is take the statement in which you are interested and calculate the probability of t given everything I know, k. And that is the answer. So if that number comes to you out of a cloud, then you're done. You don't need any of the rules of probability theory. But sometimes we need a bit of help. We need to write the probability we want in terms of probabilities we have or can get. And so a particularly useful rule is Bayes' theorem. So if I know more than one thing, hopefully, I can write k as a conjunction, x, y, and then there's Bayes' theorem, which we've seen a number of times. Now, note, we've reached this point, and there's been none of the the usual narrative about Bayes' theorem that you often see. There's no background evidence, prior likelihood. These are just labels. In particular, this is not a theory of updating specifically. It could be used for that, but there's no saying that I have a state at time t, and then I add a certain bit of knowledge, and then I condition. You can do that with this theory, but this is an identity. Any propositions will do, well, as long as those two don't contradict each other. You don't want to sort of ruin things on the other side of a... Okay, I think it'll help if I work through a couple of examples, because they'll just motivate some points that I want to make, and I'm a bit of a concrete thinker. So let's talk about Keith. This is the first Bayes' theorem application. You've surely all seen this, but let's go through it. Keith is chosen at random to be tested for a disease. The test is positive. Does poor Keith have the disease? Here's the thing we want to know, whether Keith has the disease, D. Here is P, the thing that we know that the test is positive. Let B equal all the background information. I can label it that if I want to, including the fact that 1 in 10,000 people have the disease. Also, I have the false positive and false negative rates of the test, so they turn up as likelihoods. The probability that the disease is positive, given that he has the disease, is 99%, so the test is good, and it'll only tell you positive if you don't have the disease, if that's at a 1% rate. So it's interesting to see how many of the things that we so often say about theories don't do particularly well in this case. So I have a disease hypothesis, which makes a prediction at 99% that there will be a positive test. The not disease hypothesis, on the other hand, predicts 99% there'll be a negative test. I've observed the prediction of the positive test, and yet when you do the calculation, put it all into Bayes' theory, the probability that he actually has the disease is only 1%. Now, just to convince you that that's the right answer, what's going on here is, suppose I tested a million people. Given the background information, only 1 in 100,000 will actually have the disease. I test those, and 99 will correctly test positive. The rest won't have the disease, of which most of those will, of course, test negative, because this test is pretty good, but still some fraction of that large number will test positive. And the reason why it's only 1% is because this number is so much bigger than that number. All I know about Keith is that he is in this group. And the group who have got the wrong results is larger than the group who got the right results. So note the prior in this case. We haven't had to strip back all the way to tautological knowledge. We didn't have to imagine ourselves floating in the ether, in the Platonic realm, thinking about poor Keith and whether I think he's got a disease based on no information at all. I cut what I know into two pieces, and that was enough. I had those probabilities, so that's all I did. Getting closer to some examples. that I think will home in on things I want to say about the multiverse. So there's Keith, fresh off his good luck that he probably doesn't have the disease, has now won the lottery. The chances of this are 1 in 10 million. Should we be suspicious of Keith? Now, if you're a frequentist, all you have is likelihoods, and that's a very small likelihood, so we better not use that likelihood. We better go find another likelihood. So I know what we'll do. We'll throw away the fact that we know that Keith won the lottery, and we'll calculate the probability that someone won the lottery. And thank goodness if there's 1 million ticket holders, then the probability isn't too small, so Keith didn't definitely rig the lottery. That's all you can say in that case. The Bayesian won't do it this way because this is throwing away information. So here's what the Bayesian will do. Our prior information, our background information, gives us no reason to believe that anyone rigged the lottery, or that Keith was the specific person who successfully rigged the lottery. So let the probability that someone rigged the lottery, which is 1 minus the probability that it's fair, be just some small number delta. And if 1 million people are ticket holders, but I have no information at all about who could or would want to or rig the lottery, then before I know that Keith won, or removing the fact that I know that Keith won, the probability that he was the one who rigged the lottery is then 1 in 1 million. So if you look at the ratio of the probability that is rigged to the probability that is fair, you get this, and if delta is small, that's roughly 1, and that will be not a number that's not too small. The important thing about this is that it takes into account the hypothesis that I'm interested in, the probability that this is a rigged lottery and whether I have any information about that. Whereas the frequentist method tried to test this thing without actually thinking about the other probability. One of the reasons I want to particularly stress this point is this word is a red flag to the Bayesian, where you throw information away and instead of talking about a particular person, you talk about someone. That is, as a red flag, throwing away information is usually the wrong thing to do. It gets you into the reference class problem. If you're a frequentist, you need to put things into reference classes, but you need to know that before you actually analyze your data. You need to need to know the answer before you actually do anything. Getting to an example that I think is going to hone in on these discussions we had about self-location probabilities. Suppose Keith celebrates his lottery win by buying a boat, and he's off around some islands. He has the diary of a previous explorer who reports that on island 1 there are 1 million red and 1 million blue birds, and on island B, I said 1, island A, and on island B there are 1 million red birds but only 1 blue bird. However, there's nothing in the diary that he has to indicate which of the 2 islands he's looking at is which. He alights on an island and sees a blue bird land on the beach. Which island is he on? Probably. The wrong thing to do is to say that what Keith knows is that there is at least 1 blue bird on this island. If you then do the probabilities of that, the probability that there is at least 1 blue bird on this island is 1, and the probability that there's at least 1 blue bird on that island is 1. And if it's 50-50, equal probabilities between the 2 islands, then Keith has learned precisely nothing. He still doesn't know which island he is on, or the probabilities haven't changed at all. The reason why this is, well, I'll get onto that in a second. Another probably bad idea is to propose that we need to add to the previous calculation a birdographic distribution, which is the probability that the observed bird is a particular bird. Then we can test this distribution and the hypothesis using observations, and we keep going until you get the right answer. This sounds like Bayesianism, but it has the problem of the sort of frequentist methods that you need to know the answer ahead of time, and the answer that you know already tells you what distribution to pick. Put another way, you're testing a combination of the distribution and the hypothesis of what island I'm on, but I don't want to know that. I want to know which island I'm on. The right way is to say that Keith doesn't know that there is at least 1 bird on that island. He knows more than that. He knows that this particular bird on the island is blue. Then the probability that he is on island A is 1/2, but the probability that he's on island B is about 1 in 1 million, and we get the answer that we expect, that he's probably on island A with a probability very close to 1. There's been talk about first versus third person probabilities here. I don't think that's the right distinction to make. So suppose we redo this scenario and that you are a bird with a particularly bad memory, but can read. You are on one of these islands. You read the explorer's handbook. You don't know which island you are on, but you know these facts as well. And then you can't remember seeing other birds. And then you observe a blue bird over there. What is the probability that you are on island A? Well, it's this again, because it's the probability of a particular bird. Well, let's do that whole thing again. You're a bird, bad memory, can't remember seeing other birds, but I've just learned this, and I wonder which island I'm on, and then I look at my own plumage, and I find out that I am blue. What is the probability in that situation? Well, it's the same thing again. We've just picked out a particular bird. So it's the difference between a particular probability versus a general probability, the difference between this bird and at least one bird that makes the difference. The reason why first-person probabilities are always particular probabilities, because that's what I does. It picks out the person who says it. But third-person probabilities can be just as specific, right? That bird versus me, it's the same calculation. I want to apply this Bayesian, sorry, how long have I got?
Well, you've got another 10 minutes if you want 15 minutes.
Yeah, okay, wonderful. Okay, let's apply this formalism to a specific case which is not the usual case where it's applied. Sorry, having used the word birdographic, Jim Hartle just walked in. Missed the punchline. Okay. Interesting thing about, so usually we apply this to the case where we have some laws and some data and some background information which will include perhaps the things we know about our theories, and we want to calculate the probability that my particular theory is true. There's an interesting case in cosmology where we have theories that don't directly predict data, but they predict sort of lower level theories. So inflation is the classic example. If you have the standard model of cosmology, which has the conditions at some particularly early point in the universe, that's what we need to explain all the data. And what inflation is sold to us as is a way of predicting that theory, the particular conditions there. You don't use inflation to go all the way to today. It's this idea of putting a theory on top of another one that I want to have a particular look at, because what I'm calling theory extension, I think Bayes has some interesting things to say about that. Let me just sort of build up a bit of formalism here. Let U be our observations of the universe, and let B be everything else we know. That will include all our knowledge of theoretical physics. For example, if you make a statement like in Newtonian gravity, a bound orbit around a point mass is an ellipse. That's not a statement about this universe, that's basically a mathematical statement. So that's where all our knowledge of theoretical physics goes. Let L be the laws of nature as we know them. And I'm sort of thinking of a Lagrangian here. There's a quote I particularly like from one of my favorite particle physics textbooks, which goes, "I imagine that God has a giant computer-controlled factory which takes in Lagrangians as input and delivers the universe they represent as output." So you go in there and you write out your Lagrangian, and here comes a particular universe. However, we add, you write out that Lagrangian, there will be free parameters in there which we must also specify, numbers that we need to put in, which are not predicted by the theory. These are the fundamental constants. There's also initial conditions, which is initial conditions to specify the state of a universe, to pick out one of the possible universes in the possibility space. I need to add some more information. We usually do this via initial conditions. So, in Newtonian gravity, it's the initial positions and velocities of particles. In classical electromagnetism, there'll be fields in there as well. In general relativity, it's a nightmare. With apologies to the people in the room who have written general relativity textbooks. I think I count 4. So this is the setup. So what we want to do with our theory of interest is calculate the probability of the theory given what we know. Using Bayes' theorem, this looks like this. So we have the prior probability of the theory, the what's called the marginalized likelihood. But it's particularly this term I want to look at is that L by itself does not predict data. We need those constants and initial conditions. And within Bayes' theorem, they are treated as nuisance parameters. So what you do is you assume particular values, and now I've got everything I need in this theory to predict the outcomes of observations, but I've assumed something I don't know, so I will quantify the fact that I don't know it and then integrate out that dependence. So this is a godsend in Bayesian data analysis. This is just fantastic to be able to introduce nuisance parameters like the probability that a certain hit on your detector was not a photon but a cosmic ray. You can just parameterize your ignorance and then integrate out that particular parameter. So you still get back to the question that you want to ask. So this is where the chances, so all the chance that's in a theory, this is where your theory does all its work. This is what you spend your time working with theories actually doing. The probability, you extract from them observational consequences. It is normalized over you in some sense, over observations. So if I'm about to connect up the experiment and I've got a meter, which could go somewhere from here, your theory must place its bets as to where it thinks this meter is going to end up. If it gets it right and sharp on a particular level, it will be rewarded. If it predicts a sharp probability and gets it wrong, it will be penalized. If it puts a broad distribution, then it won't be totally wrong, but it won't be as well rewarded as one that puts all its bets, puts all its eggs in one basket and they come home to roost. Sorry, that's terrible. Wow, yeah, I'm going to write that down. Let's all absorb that for a second. Okay, priors are often seen as a problem for Bayesian theory. What the Bayesian is going to say is that you are assuming things about simplicity and prior probabilities when you say that general relativity is a very simple theory and therefore we should give it a lot of attention, so that the prior probability there is an important factor. You will make an assumption whatever you do, so you might as well make it explicit. It would be nice if there was some sort of symmetry, but that's going to depend on particular problems. Occam's razor will help, and if your theory is ad hoc, which you might think of as there's a family of theories to which my theory belongs, but I've had to choose a very particular one for it to have a decent likelihood. It's got to share that probability amongst all its brothers and sisters, so it will get a small piece of the pie. There's another factor in here we need to worry about, which is the prior distribution of the free parameters. Now, you might think that's sort of coming out of nowhere, in particular because L doesn't predict it. In particular, this is where there's a number of arguments in physics. So, for example, the argument for supersymmetry that, I'm not going to be able to rehearse this off the top of my head, sorry. Fine-tuning arguments are very important in physics, that if a certain outcome only occurs for a very small range of the input parameters, of the probability of the theory, then physicists get suspicious. And I think once we have the full version of this, we can have a toy model of why this is the case. If your prior probability is broad over some particular parameter, say with range R, but the likelihood is strongly peaked over a narrow range, then this whole term here, once you do the integration, because only this bit matters, is going to be roughly equal to this width divided by that width, and is so going to be very small. Now that's a toy model, obviously, but that's what's going on with these fine-tuning arguments. And I'm not sure you could reproduce that kind of argument outside of the Bayesian framework, although if anyone's got any ideas, please let me know. Quickly moving on, at some point, okay. We can, of course, measure these free parameters. We can define some sort of range of these parameters where this now represents a range where the probability that I'm in here is much greater than the probability that I'm not in here. You don't have to do this. It'll just shortcut my notation future if I can just lump all of this together and say this is the theory of our universe. So this could be the standard model of standard model of cosmology, where Robertson-Walker space-time, and then the famous 6 parameters we've been talking about. So the case I want to look at is a theory extension. I'm going far too slowly, sorry about that. Suppose we have T, which is a new set of higher laws of nature with their own fundamental constants and their own initial conditions. What makes this an extension is the condition at the bottom. So what's going on is if I want to do, say, galaxy formation theory, I don't go all the way back to inflation. I just go back to a certain early point in the universe and go forward from there. So if I want to predict data, I don't need T once I've specified all the sort of effective parameter, the effective lower order model. So T disappears on this side. T doesn't add anything as long as I've fully specified, say, all the parameters of cosmology. This is the particular case that I want to look at. What we can do is if we have the theory extension, we ask, is the theory extension and L true, given everything we know? We might as well bundle those together. Not much point extending a theory that turns out to be false. All the things we do in our universe about the theory testing end up in one term, and then this term's the interesting one. Thanks to the condition that the theory be an extension, what's happening here is this is Bayes' theorem, except that the thing that the theory is trying to explain is the lower level theory. So that's a nice intuitive result that what inflation is trying to predict is the standard model, not directly the cosmic microwave background. As before, we'll have some nuisance parameters. So let me keep moving. One of the reasons why we want to consider other theories is that free parameters are a liability to any model in which they appear. So in particular, I've talked about the fine-tuning of for life before, that if you change parameters, things get pretty weird in the universe. There's a certain set of physicists who respond to that by saying, well, they're free parameters. We're trying to get rid of those. Who cares what happens when you change them? That this is just sort of a rallying cry. That's the fact that you have free parameters in your model is something that you must get rid of. So maybe we've got this theory, and when we use it to derive the local conditions, say you have some super particle, upper particle theory, and you try and derive the standard model of particle physics. Good luck with that. But at the point where we have a free parameter, what appears there, perhaps in option number one, is some sort of mathematical constant, which is sort of Einstein's dream. It's sort of every physicist's dream. Wouldn't it be great to derive from first principles one of the free parameters of the model? We've still got work to do if we want to evaluate this particular option. We've still got things to calculate, in particular because there's no free parameters, there's no nuisance parameters, but we've still got to take a very close look at the prior. That's not the case I want to look at. It could be the case that when you derive, you go from the upper theory down to, say, the standard model of particle physics. What appears as a free parameter in our version is actually some dynamical quantity. So say it's a function of space and time. This doesn't look particularly promising because we've just replaced a free parameter with some arbitrary function, unless we assume that it actually varies. And so the multiverse is an example of what you can call a population plus selection effect explanation, that a variegated population plus a selection effect explains some particular thing X. So the way that this usually goes is the variegated population explains why any X exists, and the selection effect explains why we observe X. You need both of those things in this kind of explanation. I won't go into the details, but there's loads of examples. It's not just a multiverse thing, obviously. Darwinian evolution, for example. Why there is a lottery winner on the front page of the newspaper. Well, lots of people bought tickets, which is why there is a lottery winner. And a newspaper editor is not going to put a loser on the front page. That's the selection effect. I'd love to talk to you about Lyman alpha radiative transfer. It's close to my heart, but I'll move on. So we need a selection effect, and this is why I had that example of first-person probabilities. Where's the selection effect when we actually go to do this calculation? Recall that the thing that we are explaining is the particular set of laws which has sort of won the contest to explain the data of our universe, where U is everything that I know. in order to explain you, these laws, say the standard model of cosmology, must refer to me. It's no good to just say there is some region of the universe in which these laws hold. In order to explain the fact that I know everything I know and that I observe what I observe about the universe, these laws must hold for me. That's why it's a particular probability rather than just a general probability. It's not just there exists some part of the universe in which these laws hold, but that they hold here. Okay? So the selection effect is sort of fairly obvious in hindsight, that the laws create the observers who observe the laws that create the observers, and around we go. The hope is that we will have a generic theory, that rather than a fine-tuned theory as we may have had before, that we will see, instead of a narrow peak, that any old sort of initial conditions and parameters of the higher theory will create a multiverse, and by that way we can have a set of parameters here which is wide compared to the prior, so we won't be in the fine-tuned problem as before. The way that the multiverse has been tested previously is via something called typicality, which has been mentioned before. Typicality, let's suppose that we do this calculation for our model and we produce a probability that we observe some particular value of a free parameter of the lower level model. Say it predicts the density of the universe. There is going to be some distribution of that. Typicality says T predicts that with 95% certainty, this particular parameter will fall within the central 95% of the distribution. We can consider this to be a prediction of the multiverse theory. If you end up here, you're doing well, and if you end up way out there somewhere, then you're doing worse. The warning buzzer sort of rings in your head that we've tried to test a theory using its likelihood alone, so that this is looking an awful lot like frequentism. So in Bayesian terms, typicality is neither a sufficient nor a necessary condition for a theory to have a high posterior probability. So remember Paul Keith, his positive test is typical of the diseased hypothesis, but that doesn't mean that he probably has the disease. Using Bayes' theorem, we can work out when typicality is useful. If we have two multiverse theories that have a similar prior probabilities and the width of the likelihoods is similar, then the theory for which the predicted parameters lie closest to the peak will have the greatest posterior probability. The problem is that what we're doing here is we're comparing different parts of the same theory when what we're really trying to do is compare different theories. Let's be clear about what this is, and I'll try and rush through the rest. In most Bayesian textbooks, you will find derivations of the classic statistical methods, the orthodox frequentist statistics, given certain assumptions. This has sometimes been presented as a problem for Bayesianism, that while orthodox statistics has these methods, Bayesianism must make extra assumptions and then somehow motivate those assumptions. As if what the Bayesian was doing was looking up to the frequentist for validation of his position. All right? Perish the thought. This is not looking up for validation, this is looking down in condescension. The Bayesian has taken time out from his busy day to highlight for the frequentist the assumptions that he is making behind the scenes. You then get that feeling of control I was talking about before, that we have the right question to ask and we know exactly the circumstances under which these otherwise not ridiculous things to do, the frequentist methods will work. This is the kind of thing that typicality is a frequentist methods, and using Bayesianism we can look at the conditions under which it is a useful thing to do. It is not a completely ridiculous thing to do, but it is neither sufficient nor necessary for a multiverse theory to be a good theory. What we really want to do is calculate the whole catastrophe. I'll rush through this far too quickly. Because this theory predicts an actual population from which you are a subpart of that population, the likelihood is going to be a frequency. So this has been noted a number of times. The way that you calculate that in the particular one-dimensional case is you calculate the total number of observers, you calculate the total number of observers who observe a particular value of the observed parameter that you have seen, and then because this is just a population, the probability is then just the ratio of those two, and therein lies the measure problem. If those are both infinite, what do you do? We can discuss that later. I don't think Bayes' theorem actually comes down on either side of the debate that was had before. What we'd particularly like is for that number to be large, the number of observers who observe what I observe. So if we look at, this is very sort of rough, but a particular per unit time, per unit volume rate of producing observers as a function of that parameter, it's going to depend on how fast particular parameters produce observers, and then you add them all up over the universe. This term, we want that to peak somewhere near where we are. So this is the fine-tuning of the universe for intelligent life. That seemingly small changes in the free parameters of the laws of nature as we know it seem to have dramatic, uncompensated, and detrimental effects on the ability of the universe to support the complexity needed for physical life forms. As Bernard mentioned before, I have a review of the literature on this. As one particular example, here is a set of the up quark mass, the down quark mass, there's the Planck mass, and there's a lower limit. If we zoom in on the part of this space where we are, that's us there. This is our now region of parameter space. And we could do something like say, how many elements in the periodic table are stable and will actually be produced in stars in these universes. And in all these regions, you get 1, 1, 1, none, none, 1, 92 in that tiny little square there where it all comes together. We are, of course, in there. What this suggests is that this particular function, the rate at which we're producing observers, is peaked somewhere near, not where at the top, but so we can see vast wastelands where that particular function seems to be an awful lot lower than where we are. That's as much as a claim as I want to make. What that suggests is that this is probably a necessary condition for this whole scheme to work, and some of the pieces seem to be in the place for this. Tom reported to us that there are certain parameters which one might expect from a string theory landscape. I want to request it, sorry. No, let's not do that. The Boltzmann problem is the fact that most of space-time volume is somewhere else. This is the problem of Boltzmann observers, what you might say, so if I do the likelihood of a particular value, here's where biological life is, that's great, it looks nice and peaked, which is the fine-tuning, but if rare observers can observe other, they all add up, even though they're freaks, there's so much space there for them, then the likelihood is not going to be there. This is not the problem of Boltzmann me's, that there will be copies of me out there. That's a separate problem. Let me finish just by saying this idea of theory extension, at no point did I assume that the theory T is any sort of physical theory. If you wanted to put in some other kind of speculation, big C cosmology speculation, go ahead, feel free and see what comes out the other end. There's my conclusions. I think, Bayes. Probability from principles is really why it's so attractive, and why I think philosophers who really sort of slow down and pull the arguments apart and think about this have a lot to sort of add to this. I mean, this is the philosophy of probability, of course. I've talked about first and third person theory extension as a way of eliminating free parameters, fine-tuned versus generic theories. There's sort of varied population plus selection effect explanations. I think we can get a good handle on that. Typicality in the Bayes framework, we can understand the conditions under which that's a good idea, and we don't have to worry about Boltzmann brains anymore. I don't think Bayes has anything particular to say about the measure theory, and if you want to do big C cosmology, then good luck to you. Thank you. Sorry, I wanted to finish with more time.
Thank you, Luke. We have about 5 minutes for questions. Don.
From what I understood of your talk, I think I agreed with virtually all of it, but I thought I'd check the comment. If you happened to be at the early part of my talk, did mine seem to fit in with yours? And
you seem to be collapsing things down to probability 0 and 1 for likelihoods. That's a special case, but I think, it's possible that when we know the complete theory, it won't necessarily give us 0 or 1 as an answer for any particular thing, but
yeah, I mean, I guess I was proposing this measure, which is analogous to what you said about the frequency. But do you agree that for the likelihood, you really should normalize the probability over all
Absolutely.
possible observations. You don't just do it
Yeah.
over the fact that we get that observation, and the other possibility is that, well, that our observation exists and that our observation doesn't exist. I mean, you agree that...
I think those are the same. No,
No, not quite, because there may be many of them that exist.
Yeah.
I mean, and there may be, you have an observation, I have an observation, so on. And I'm advocating that that for your observation, you shouldn't just calculate the probability it exists plus the probability that your observation doesn't exist anywhere in the universe. But I'm advocating that that the possibilities are your observation, my observation, his observation, Boltzmann brain observation.
Right.
Each theory should normalize some of
yeah.
those
I think
problems.
I agree with that, yeah.
Yeah.
Okay. Bill, Andrew.
In your bird example, I'm just wondering what you do when I give you some additional information.
Conditionalize, sorry.
Wait, I haven't given you the additional information yet.
Go for it.
It turns out that all the leaves on both islands are red, of exactly the same color of the birds, and he observed in the evening when all the birds were roosting.
Okay, yeah, so you've got to think about what you really know. So,
Everything except that addition.
okay, in that case...
Everything you knew except this additional information.
If I use this as is exactly stated, I'm saying that I definitely saw a blue bird land on the beach. And I definitely know this. If you want to step it back a level, you could say, I saw something blue sort of flap over there somewhere. And then you can just fold that into your model. What is the probability that that blue thing was a bird? It's harder to estimate that, but so there's always the way you can always step back and say, all right, what did I know? Do I really know that I saw a bird or that it was a bird?
No, the question isn't
I'm not.
The question isn't whether it was a bird, but the question is whether or not he could see a red one.
Oh, okay. But he still knows that the particular bird he saw was blue, but he couldn't have seen a red bird if it was a red bird. Is that what you... Right. Okay. You do the calculation, and I can't do it off the top of my head. I think nothing changes in this particular setup. He really did see a red bird. That's what he knows. Something that he could have seen but really didn't, just doesn't come into it. It's doing the best I can with what I know. The likelihood should take into account what you can and cannot observe.
Okay, another problem for you.
Yeah, so I'll just try this one more time. So let's do the medical test case, right? So, but here I wake you up in the middle of the night and I tell you there's a disease, and I'm going to give you a test for it, and it's the same. I got a 99%. Let's say it's like a 90% specific and a 90% what's the other word? Specific and sensitive test. Yeah. What do you think is the probability that you have the disease?
The prior probability?
No, what do you use as a prior?
Is
it 50-50 because you're ignorant?
This is a very good question. I think Bayesians view this. I could try and answer that particular question, but there's always another example of what do I do with my ignorance, right? I think this, within the Bayesian formula, this is a hard problem, but not a fatal error. That what I'm trying to do is characterize a certain state of knowledge. And so, as I said before, ignorance should not derail the project.
The worry isn't that ignorance should derail the project. The worry is that ignorance should be modeled by a uniform distribution always.
So I think this was sort of, not being a philosopher, I only know that I'm really hitting on philosophical problems if David Albert looks worried. So he's been having a go, we've been back and forth about this. I think the worry is that what this whole scheme seems to be doing is alchemy, that I'm converting the base metal of ignorance into the pure gold of a very specific probability assignment. Given that the whole idea is to characterize a certain state of knowledge, I don't think, in particular, given that it doesn't say anything about the world itself, it's not a physical probability, I don't see an in-principle problem with this kind of thing, although there are always going to be hard cases. Go on, Chris.
Yeah, I'd just like you to say, oh, Chris Smink. I'd like to hear more about the context in which you think an assumption of typicality or maybe a bird-graphic distributions are appropriate, because you said later on in the talk, like, look, this is an example where the Bayesian can tell the frequentist where certain assumptions they make are actually reasonable. And you said a little bit about it, but I didn't fully get it. So if you could just say again.
I think that typicality is not a separate assumption, and that what's been called the zero-graphic distribution is not a free thing. That given a certain state of knowledge, there is an answer there. It might be hard to find. In this finite case, it's easy. It's probably just 1 over the number. But that if the project is to quantify the state of knowledge, then the zero-graphic distribution is about a state of knowledge, and it's all happening upstairs. I just need to think hard.
Can I ask a question, Luke?
Yes.
In the context of the multiverse, say we wanted to compare the Smolin multiverse, where in fact nearly all the universes are suitable for the constants that make black holes, to the normal multiverse where it's a tiny fraction, which seems to me rather analogous to the bird problem. I mean, how would you go about deciding which is the most plausible multiverse model?
Well, I mean, I think what you're saying is the Smolin multiverse, that thing peaks near where we are, and so it will be rewarded for a correct prediction. I mean, this is just the likelihood, but if you hit that peak, you've done well. You'll probably do better than a lot of other theories that don't quite hit the peak. I'm doing theory testing. I'm not really trying to. There's no point of actually trying to build a model or actually test some multiverses. I just want to know what questions we need to ask within this framework.
Well, I think we'll just have one more quick question if you...
Okay, I just wanted to flag the assumption that you're making on that very slide, which is that when the numbers are finite, the relevant priors are got by taking the proportions. I think that's an attractive view, but you might think, but I think there's another view that has something to be said for it, where you say, oh, simplicity matters. That counting measure is a simple measure, but there may be other simple measures around. I don't know if there's any real-life cases where the difference between these two perspectives would matter, but like here's an example. So here's another fairly simple measure you could choose. Take the total mass of all of the people take the proportion of the mass of all intelligent life that has the property of interest. If we found ourselves to be surprisingly massive compared to all aliens, then that would be surprising if you're taking priors by counting, but unsurprising if you're taking priors by adding up total mass. And if we're trying to choose between different theories about what the aliens are like, that might really matter. So I just wanted to flag that as a place where you've made a very you've taken sides on a very interesting issue that can be very succinctly expressed within the framework you're using.
Right. I think within a sort of a population plus selection effect kind of explanation, the question is, what are the members of this population? And I think the total mass just isn't a measure of that. In particular, I still can't give up the permutation symmetry of the problem. That the house example in the finite case, nothing should change if I shuffle the houses. I'm still in the same house, everyone else is in the same house, so the probabilities I assign should be the same if, given the shuffling. That uniquely gives this, and fails, trivially in the infinite case. I'm still thinking that through. My point is, that the measure problem, I don't think Bayes has anything to say about that. It's really from the theory. You're going to have to think hard about the theory.
Okay, thanks, Luke. I'll have to end this talk now, but thank you very much. I think we learnt a lot.